In section 5.3, we'll learn about higher derivatives, like for example, second derivative, third, and so on, because the first derivative is not the only derivative that you can take of a function. So higher order derivatives, concavity, what does that represent? That's like shape of the graph, and also second derivative test, which is alternative to first derivative test for maxima and minima. Once again, I recommend actually reading through the section. Here are some helpful examples before class on Tuesday and so on. So far we've learned about derivative as a rate of change of a function, but what if we'd like to know how the derivative function is changing? For example, the velocity is known as rate of change of distance over time. But what if we would like to know how velocity is changing? For example, are we accelerating? Does the velocity increase? Or are we decelerating? Does the velocity decrease, for example? So we may need to take derivative of the derivative, or in this case, derivative of velocity. It's also known as acceleration. So acceleration basically measures how is the velocity changing. So again, are we speeding up? Are we slowing down, etc.? So this brings us to second derivative, which is going to be very important for us as well. Second derivative means a lot about the original function and also the first derivative. It gives us a lot of information. So basically, it's defined as derivative of f prime of x. So if you find f prime of x, the first derivative, take derivative again, then you'll find second derivative. It's like a domino effect. Sometimes you'll see it as f double prime of x. Sometimes you'll see it with a little square. Basically, it means, we write it like that. Basically, it means d of dy, which is why it's squared, over dx squared. You'll see sometimes an acceleration has really strange units. Like, for example, feet per second squared. You'll see how the time is squared, because basically it's feet per second, let's say it's velocity, per another second. So how is that changing over time again, which is why seconds are squared, and etc. So once again, I think I've already covered this. To find second derivative, we can find the derivative of derivative, and so on. And we can also find third derivative, which is f triple prime of x. We can actually keep going down. Fourth derivative, I think we stop using these kind of Roman numerals, and we can actually use the little 4 and 5 for the fifth, and so on. So you can keep going down, but I think you get less information. Second derivative gives us a lot of information. Third and fourth, it depending on what you're looking for. You can do that as exercise, but we'll actually find the higher order derivatives, but mostly we'll stick with second derivative with some applications and a lot of significance, and see what happens there. So in the next few problems, let's practice calculating second derivative. So let's say if we have y equals to negative x squared plus x, then y prime, the derivative of original, will give us negative 2x plus 1. Then what's the derivative of that, or y double prime? Well, that's just negative 2. So notice with polynomials, you don't have to go too far before you get 0. That's just with polynomials though, not true about other functions. Say we have negative 2 over x squared, just like with any derivatives. First put it as a negative exponent. Then you can find first derivative first, which will become positive 4x to the negative third power. Now let's find derivative of that. That's y double prime. That becomes negative 12x to the negative 4. So notice how x keep getting more negative all the way throughout. And you can put it back in denominator to kind of keep it in line with the original. So we get negative 12 over x to the 4th. You can do the same thing with exponentials. Let's say e to the negative x plus e to the x. Once again, find first derivative first. So if you recall, the derivative of exponential is itself, it's e to the negative x times the derivative of the exponent, which is negative 1. I already moved it to the front, so it becomes a negative, plus e to the x is basically the derivative is just itself. So e to the negative x will keep changing signs, as you'll see, but e to the x will stay the same. That's first derivative. You can pause it, see if you can find second derivative. If you come back, and you'll see it's the same idea. So negative keeps as the exponent. I actually So this is the final answer, but you'll see if you actually get this final answer. So we keep the negative, but because we're going to be multiplying it by -1 again because of the chain rule, negative and the negative will end up canceling each other, so you will actually get positive e to the negative x. So as I already mentioned, it alternates. So you do have to show some work here, but basically you'll get positive e to the negative x plus original e to the x. Notice it's actually the same as the original function. Interestingly enough, that can happen with exponential functions. So it will keep alternating. I think third derivative would give us negative again, and so on. So try working it out, see if you get the same answer. Now, again, you can do this with log functions too. So notice you'll see a lot more e to the x and ln of x than other bases. But let's try it with 1 over x minus ln of x. Put it 1 over x as x to the -1 power and take the derivative. So first derivative is negative x to the -2 power minus derivative of ln of x is 1 over x. So we'll get negative x to the -2 power minus, I put it as a negative because we're going to be taking derivative again. So I put it as negative exponent. So second derivative, once again, you could pause the video and try to work this out. But what I get now, -2 comes down and cancels this negative. So we'll get positive 2x to the -3rd power. And then what's the derivative of negative x to the -1 power? -1 times this negative will become positive x to the -2nd power. And once again, because original had fractions, so we can put them back in denominator, we'll get 2 stays on the top, x to the 3rd goes to denominator, becomes positive, plus 1 over x squared, makes it positive. That's the second derivative. Now let's practice with some applications. For example, acceleration, that's a common one, but we'll see some business ones in just a little bit too. Let's say the position s, which is basically distance, of a point in feet is given as a function of time t in seconds. Find a, its acceleration at time t, and b, its acceleration at the specified time. So we're given the position function, and t equals 2 seconds, and basically it's application of second derivative. So acceleration is derivative of velocity, or first derivative. So first we find velocity equation, which is s prime, and that's, if you notice, -12 is gone, derivative of t is 1, and then -16t squared becomes -32t. Then what's acceleration? It's double prime of position function, and that's basically just -32. So notice here acceleration is constant. That tells us that we keep decreasing at a constant rate, let's say if the object is falling. And so that's the function. Now if you recall, it was just a constant, so if we plug in 2 into acceleration, because it was -32, there is no t, it still stays -32 feet per second, that's what I mentioned before. So that becomes feet per second squared. Again, these are just the units of acceleration. Now, we'll learn to apply a second derivative to something called concavity. It's something about the graph that we're going to follow up in the next section. How does the graph look? How does the second derivative affect the graph? We have two definitions, concave up and concave down. Let's focus on concave up first. You can have an increasing function and it follows up like this. So basically these are parts of the U. Looks like an a right side up parabola basically. So this is decreasing part, sort of looks like exponential a little bit. This is decreasing, so any parts of the U looks like concave up. Versus concave down, if you notice, again, this function is increasing but in a different way. A little bit more like a logarithmic function or maybe radical. It looks like part of upside down U. Again, it could be increasing or decreasing or doing the whole thing, with including the maximum. So we have concave up and down. Inflection points is where the function switches from concave up to down or vice versa. So for example, you may start with concave down and then all of a sudden switch right at this point. Visually we can see this is where the inflection point is, so it switches to concave up, or vice versa. Start with concave up, reach this kind of point, and then become concave down. So you can take a look at the graph of the function. We'll probably do this in class, but you can visually see where the inflection points would be and what the concavity is. So we'll do these problems in class. We'll come back to them, but these are the answers for these problems. Now, I would like to do, we'll come back to concavity points in a little bit, but what about second derivative test for maxima and minima? So here's how it works. If x equals c is a critical number or point that we've done before in previous sections, and if it's stationary, now this only works for stationary points. Unfortunately, it does not work too well for singular or endpoints. So first derivative test is definitely very important for us, even though it's a little bit longer. But remember, in a lot of applications in the previous section, a lot of the points were stationary. So this is another quick way to basically check them very quickly. So if we have this critical point, and if we plug it into the second derivative, if we get negative, that means, what does that mean? It means the function's concave down. This is something I forgot to mention, but if the function's concave down, then the second derivative is negative. If it's concave up, second derivative is positive. So that's just something. Sorry, I had to pause the video. Let me actually go back to the original definition of where it's concave up or down. So yeah, if it's concave up, the second derivative at that point is positive. That's what we know. If it's concave down, the second derivative at those points, or that portion of the graph, is negative. At inflection point, it's 0, but the concavity has to switch. So if you actually put that point with a second derivative on the number line, if it switches sign, again from positive to negative, or from negative to positive, then we have an inflection point. So the concavity has to switch. So just because it's 0 at a certain point, that's not enough to mean that it's going to be an inflection point. So what has to happen, the concavity has to switch. I think we'll use this more in the next section when we're actually going to talk about graphs of functions. But anyway, going back to the second derivative test. So if second derivative at that point is negative, we have concave down, but it actually means we have a maximum at that point. Or vice versa, if second derivative at that point is positive, it's actually concave up. You can actually draw it like a little parabola, so that means we have a minimum. Now, what happens if it's exactly 0? Well, it may be a possible inflection point, but you have to check it with second derivative, and so we have no information. Basically, the test fails, and you have to go back to first derivative test or some other way, like graphing calculator, to figure out if what happens at that point. So here are some examples. So in this case, for the next few problems, find x coordinates of all critical points of the given functions. Determine whether each critical point is a relative max, min, or neither by first applying second derivative test, and if the test fails by some other method. So it's basically putting it to practice what we just learned. If we have a function, again, it's finding maxima and minima. It all comes down to that. Again, in this section, we can find critical points. Again, we can take the derivative. Again, there would just be stationary points because no interval is given, there are no endpoints, and there are no singular points. The first derivative is always defined. We find x, it happens to be a half. Now, how do we apply second derivative test? We need to find second derivative, which is derivative of 4x minus 2. So 4x becomes 4 and negative 2 is gone because it's a constant. And again, second derivative happens to be a constant. So no matter what you plug in, let's say a half, we'll still get 4, which is positive. And if you recall, what does that mean? That means we have it's concave up and we have a minimum at that point. So again, that's how quickly it is. If you have a single maximum or a minimum, you can use second derivative test to verify it. With higher order powers, the second derivative may not be constant, so let's see how that works. 3x to the fourth minus 2x cubed. Again, you can take first derivative. We'll get 12x cubed minus 6x squared. Once again, set it equal to 0. As before, you can pull out 6x squared and solve. We'll actually get 2 stationary points, 0 and a half. Now we need to find second derivative. Again, going back to first derivative, we'll get 36x squared minus 12x. Plug in 0. Now note we get 0, so a second derivative test fails. We have to check with some other derivative. So yes, it can happen. Maybe you wouldn't have an extreme point at that point. 1/2, I plugged it in and I actually get positive 3 because it's 36 times half squared. That means 36 times 1 over 4, which is 9. And then minus 12 times the half is minus 6, which is 3, and it's positive, so we have a minimum at that point. So what happens at x equals 0? Remember how we can go back to the number line, which is first derivative test. Plug 0. I pick a couple of points because a half is so close to 0. I think I picked 0.25 to check. So I plugged in negative 1 and 0.25 into the first derivative, which is right here. So if it's negative 1, remember how we can plug in both the front and in parentheses. Get positive because it's x squared, but inside of parentheses negative 1 will give us negative, so the whole thing is negative. If I plug in a quarter, again, outside of parentheses is positive because it's squared, but inside of parentheses 2 times a quarter, that is actually like a half minus 1, it still will give us negative. So we do not have an extrema at that point, which is why the test failed. And so we just have a relative minimum at x equals 1/2. And again, we can find y values by plugging them back into the original function. And that's it for this section.